Hi, everyone. Welcome back. Hope you had a good time. So I just want to thank you all for joining us tonight. And as you can see, I had my first costume change, which means it's the party time of the day now. So I just want to thank our sponsors again, Container Solutions, Equinix Metal, Cycloid, Giant Swarm, Instana, and Kinfolk. So for our next speaker, I don't want to even say that much. All I'm going to say is that he wants to play a game with us. So Adam, take it away.
Everyone. Hello, everyone. Let's play a game. My name is Otto. I'm a cloud native engineer at the company called Container Solution. And today I will be speaking about Kubernetes bugs, which can actually give you a heart attack. So let's go through it. So agenda, we already passed the intro. So here a quick overview of what we are going to talk about. So we are going to talk about two bugs in the Kubernetes, which can actually break your production or your whole Kubernetes cluster. So we'll be speaking about involuntary denial of service, and then we'll proceed to the purge of pods, and we'll finish by some final thoughts. So let's get into involuntary denial of service. So this is a bug in the Kubernetes, which can actually cause your control plane to totally break down. So to the point that it is not usable anymore. So let's get into details. So this is actually a bug in the kube-controller-manager. And it is happening when you assign a pod to the node, and this pod ends up in the failed state. So if it occurs, then the kube-controller-manager will actually continuously spawn new pods. And the important thing to note here is that the pods are going to be spawned at the full speed. So what does it mean is that the API server is going to be under high pressure to the point that it can at some point stop responding to the client requests. Another thing that is important to note here is that those pods which are created by kube-controller-manager, they're like filling up the etcd storage. So this bug was reported already a few times. So I gave like a list of the issues that you can find in the GitHub Kubernetes repository. I will share those slides later on. So you can, if you are interested, you can just follow these links and have a look into what other users were reporting those. So how to actually trigger this bug? So I managed to identify two methods for triggering. So as I mentioned earlier, the key part of triggering is that the pod must end up in the failed state. So one way of doing this is to actually define unsupported option in the pod definition. So for example, if our kubelet was configured the way that it does not support the sysctl, and we define this we define those sysctls option in the security context of the pod, it will trigger this behavior. Another way of triggering this, which is a little bit more hacky and requires more like a workaround to get this triggered, is actually to schedule pod directly to the node, and in the request or limits specify the CPU or memory limit value higher than the CPU count or memory size of the node. So without talking too much about this, let's actually try to trigger it. So I have I prepared the Kubernetes cluster in the Google Cloud. So this is standard Kubernetes cluster that you can with the default option. So no magic there. It has 3 nodes. So let's just jump into it directly. So just to show you that I'm not lying or anything. Yeah, we have a working cluster. Let's get nodes. So yeah, so in order to trigger this bug, I prepared a deployment with this sysctl special condition in order to trigger this. So yeah, the standard deployment, you can see a lot of A's. The reason for all those A's is actually to speed up the final result. so we can actually see it during this talk, because those A's are, as a consequence of those A's, the size of this object is 65 kilobytes, which is like the limit of the size of the object that you can store in the etcd. And what you can see here is that I specified the security context. Even I did some typo here just to underline how trivial it is to trigger this even with a simple typo in your deployment. So let's actually apply it to the Kubernetes. Oh, good. Yeah, as you can see, this is like spawning continuously the pods, and it will keep to spawn pods till the control plane collapse or till the etcd is the etcd storage is completely filled up. So let's get back to the presentation and let's discuss what's happening in the back of this, behind this bug. So let's have a quick view on the culprit. So once we created the deployment and persisted this in the kube API server, the deployment was translated into the replica set. So then the replica set pick up the instruction from the replica set resource and started to create pods. Once the pods were persisted in the Kubernetes API server, kubelet tried to pick up those instructions from the pod, so it can communicate to the container engine what kind of the container should be created. But since there is like a problem with the instruction, the kubelet is unable to deploy those pods onto the node, so it marks them in the so-called failed state. Unfortunately, the replica set controller is unaware of the failed state of the pod, so it just keeps thinking that there is not enough pods, so it just keeps on adding those new pods to the Kubernetes cluster. And yeah, this is what's happening there behind in the code. And what we can be interested about is how to prevent it. So the easy answer for this is the resource quota. So what are resource quota? So this is like built-in validating admission controller, which is enabled at the API server. So this actually ensures that the requested pods do not exceed enforced limits. So for example, like the CPU or memory, but also we can actually limit the number of the objects that we are storing in the etcd. So in order to achieve it, we have to use the following syntax, which is count/pods or any other resource. So as a result of this, we will have only a limited number of the objects in the etcd for specific namespace. So thanks to this, we can like avoid avoid to put too many objects in the etcd and to avoid collapse of the control plane. Another way, which is more complicated and more complex, is actually to implement validation webhook, so we can prevent users from using the forbidden options. This could be achieved by using something called open policy agent. Yeah, and now let's talk about what's the impact of this bug on the managed clusters. So in the Google Cloud, we'll see shortly that the whole monitoring components will be killed by out-of-memory manager. And at some point, hopefully, I'll be able to show you this, that the whole control plane will start to time out. In the Azure, we can see something like memory overcommitment. This is tied to the fact that the Azure managed pods, they don't have any request limits or resource limits or resource requests. So we can see that the memory use is over the actual size of the memory of the node. And as a consequence of it, we can see like monitoring pods being evicted from the node. I haven't seen any impact on the control plane in the AWS. The only thing which is worth mentioning is the log spam, but this is something that we could actually predict from this behavior. So this is it about the involuntary denial of service. Let's get up to another bug, the purge of pods. That's an interesting one as well. So this bug is actually has its source in the kubelet. So, but it requires your application actually to behave wrongly. So it requires your application to keep writing to the deleted file. So if your application keeps writing, it is also filling up the ephemeral storage that your containers are stored. So at some point, it will trigger a condition which is called node has disk pressure. But since we are writing to the already deleted file, from kubelet perspective, the offending application does not use ephemeral storage at all. So as a consequence, the kubelet is randomly evicting the pods from the node. So as in the previous bug, there's an issue which is mentioning this in the GitHub Kubernetes. So how to trigger it? So this is exactly what I just said, that we need to have an application which is badly written and which actually creates files, starts writing to it, then deletes it somehow, but keeps the file handle open and continue writing to this. I created proof of concept for it. So if you want to play with it in your sandbox environment, feel free. So this is the result that I could observe in my home laboratory. So my home Kubernetes cluster, and I just spawned like a lot of busy bugs which were like randomly evicted from the node which was under the disk pressure. How to prevent it? So there is no easy answer to it because from the kubelet perspective, it's not so easy to implement a fix. But a quick solution that we can think about is actually to use priority classes. So give a higher priority for your critical workloads, so they are not evicted in the first order. But the second and even the more important one is to actually ensure that your software is properly tested, so you avoid this kind of behavior in the future. So this is it from me. But let's have a look at our denial of service before we go home. So as we can see here, it stopped at some point. So let's just try to figure out how many pods were created by counting the lines. Okay, it will take some time. So in the meantime, we can see if the workloads are. We can see the workloads from the engine. Okay, it takes time. It takes time here too. So I guess we can already see the effect of this bug on our cluster in the GCP, that the requests are taking lots of time. And here we are actually seeing that we have like real impact on our cluster, because we are unable to, well, the Google web browser or whatever is behind it is unable to get all the workloads from this cluster, so which is bad. Here we have 249 pods, and it will try to keep and put more, but unfortunately the control plane is already under such pressure that that's not going to be a case. Okay, so it's still responding, but I can assure you that if we wait like 2 more minutes, which unfortunately we don't have, we'll see the control plane being completely unresponsive. If you are interested in this and want to see it actually, then just feel free to reach out to me on the Slack or in the Brella. So that's it from me. Thank you for listening, and see you around. Cheers.
Thanks, Adam. That was great. And you didn't you really held to your promise, because that was really scary. I think those bugs really gave me some kind of mental disease or something. Yeah, also in the chat, I'm seeing Anonymous saying, thanks, Adam, nice demo. So I think we might have time for like one short question, which would be from me. And I would just like to know if you know of any like real production like effect that these specific bugs that you've shown us have caused, like any kinds of platform that was taken down by like a bug like this.
Unfortunately, personally, I never met this, so I had a lot of luck. But if you go in the issues that I mentioned in the GitHub, you can see some people actually they mentioned that they were hit very badly by especially the first bug. So
Yeah, for
there is
sure.
definitely something you need to pay attention to.
Yeah, absolutely, because that is, again, it looked very scary. Thanks so much for joining us and for speaking about this.